Hello students, in this video I would like to discuss a very interesting approximation technique with you guys, and this approximation technique is called Newton's method. Let me mention that Newton's method is used to approximate the zero of the function. Alright, so let's begin this discussion by understanding the formal definition of a zero of the function. Alright, so here is the definition. A number r is called zero of the function f of x if f of r equal to 0, meaning that a number is called zero of the function if you plug x equal to r into your function, that result into 0. Alright, so in other words, that this equation f at r equal to 0 needs to be satisfied in order for r to be the 0. You guys have calculated 0 of many polynomial function throughout the semester in this course. Let's try to recall one very simple example. Here is a problem that you guys may have seen quite a few times. All right, compute all zeros of function f of x equal to x square minus 3x plus 2. All right, again, if function is given, how to calculate it 0? Well, set your function equal to 0 and solve the equation for x. Alright, let's do it. To compute the 0 of the function, I'm going to set my function equal to 0, which means I'm setting x square minus 3x plus 2 equal to 0. Well, what is that? That is a quadratic equation. We have solved it many times in this course, right? It's a monic polynomial. Coefficient of x square term is 1, right? Let's factorize this. Factors of 2 whose sum is negative 3 looks like negative 2 and negative 1. Because the polynomial is monic, I can write down factorization directly. Use that zero divisor property. Product of two factor becomes 0 only if one of those two factor itself is 0, right? So this means x plus 2 has to be 0 or x minus 1 has to be 0. Look, I get linear equation in x, very easy to solve, right? Add 2 on both sides to solve the first equation for x, add 1 on both sides to solve the second equation for x. That really gives me 2 zeros of the function x square minus 3x plus 2. Now, here is the question. Is computation of 0 always easy for every function? Think about it. Answer to this question is no. Most of the time, when you have a function given in terms of higher degree polynomial or in terms of exponential or logarithmic function, it is very difficult to calculate the zero of such function. Alright, so here is that remark. In general, it's not easy to compute the zero of the function. Alright, computation, for example, consider this function x to the 4 minus 7x plus minus 7x minus 2. Right, computing 0 of this function is not that easy, right? Factorization technique is not gonna help here. Okay, so the question is there any other way that we can compromise a little bit, but we can get close to the 0 with close to the 0 of the function? Answer to this question is yes, and as you know, the answer is use the Newton's method. All right, now before we use Newton's method, I would like to explain you what works behind this curtain. All right, so the result that we need to study before we study Newton's method is intermediate value theorem. This is the theorem that is on the back of Newton's method. All right, let's try to understand what this result says. All right, let f of x be a continuous function on interval a to b with f at left end point gives you a positive entry and f evaluated at the right end point of the interval gives you the negative entry. Right, meaning that function changes from negative to positive as you move from a to b, or function changes from positive to negative as you move from A to B. Alright, so sign of your function must be changed in the interval. Alright, if this is happening, then because of continuity, function is continuous. Remember, the graph doesn't break, no jumps, no asymptotic behavior, no holes are allowed for continuous function on the region A to B. Alright, so if f of A is negative and f of B is positive, then as your function move from A to B, it must cut somewhere your x-axis. Alright, and this is a very clear and simple idea. Alright, so that's what is written here. Then there exists a point C in interval A to B where f of C takes the value 0, meaning there is a point C where the graph of the function cuts the x-axis. Let's understand this with this result with this picture. Look at this. The function is continuous from 2 to 4. Right? Function is continuous from 2 to 4. I want you to notice carefully that value of my function at 2 is negative. Value of my function at 4 is going to be positive. Function changes a sign from negative to positive as I move from 2 to 4. Alright, meaning that there must be some point in between 2 and 4 where graph of my function cuts the x-axis, meaning that C is the 0 of the function. Alright, so as you see the graph, when you see the graph of the function, it makes a complete sense. Look, this is the 0, right? Understand that if you consider this interval from 0 to 1, right? Function value at 0 is positive 1, function value at 1 is negative. So value changes from positive to negative. So there must be one point in between 0 and 1 where the graph cut the x-axis, meaning at x-axis your function value is 0, right? And this is the 0 of your function, right? Very interesting result, very clean result, you know. So this is behind that Newton's method. All right, the question here is, can we calculate that 0 algebraically? Answer is yes, we can calculate this 0, we can at least approximate this 0. Okay, question is how. We have this interesting method called Newton's method that will allow us to, you know, approximate the 0 of the function. So let's understand what do we mean by Newton's method. Here is a statement of Newton's method. Let f of x be a continuous function on interval a to b, and suppose your function changes a sign from positive to negative or negative to positive. Remember, this is a necessary condition. You need to check this on your exam and on your quizzes, so be sure you know that this is a necessary condition together with continuity to have a 0 between, you know, a and b. Okay, alright, so let's say our function is continuous on a to b, and let's say my function changes from negative to positive or positive to negative on interval a to b. Then a 0 of function f of x can be approximated using this iterative formula. C of n plus 1 is obtained from cnth 0 using this formula, c sub n minus function evaluated at c of n divided by derivative of the function evaluated at c of n. Again, like Euler's formula, this is an iterative formula, meaning you need to start with your initial guess C0. Alright, our standard choice for C0 will be the left endpoint, but if you start with right endpoint of the interval, or if you start with somewhere between that interval, that will be fine too. Alright, so again, I would start the process with one simple point inside a and b. A might be the ideal choice. Okay, so cn plus 1 is Cn minus f of Cn minus f prime at C of n. Alright, f prime of C of n, you need it to be non-zero in order to make this thing a sense. Okay, alright, so this is really the statement called Newton's theorem. Remember, we need two things: continuity of the function and change in the sign from a to b. Alright, then 0 c can be approximated using this formula. C sub n plus 1 means n plus 1th approximation of this actual 0 can be obtained from nth approximation using this formula: Cn minus f at Cn divided by f prime at Cn. It's clear that I need a function and its derivative to be evaluated at, Cn, approximated nth approximation of C. Okay, alright, so as I mentioned, Newton's method is an iterative method like Euler's method. We need to start with C0, and based on that we are going to go close to actual solution using this formula. Okay, most of the time we will be approximating the 0 up to 3 decimal. Alright, so if approximation is 3 decimal accurate, then that's when we will stop. And normally third or fourth iteration gives you this value. Anyway, let's try to understand what we are going to do in general. Okay, so here is a general step-by-step idea to use Newton's method. Step 1, be sure that the right side of the equation is 0. Alright, sometime you will not be given equation. You have to form the equation by yourself, and I'll give you some examples today in this video to clarify it. Okay, so if for example you are given equation, then what you need to do is make sure that you shift everything to the left side. Right side needs to be 0, because that's the most effective way to solve the equation, right? So if 0 is on the other side, we can easily solve it. So we wanted to make sure that the right side is 0. Step 2, I want you to label the left side. Remember, only left side is labeled as a function. Alright, so function is an expression, should not include equal to 0. Only left side of your equation is labeled as f of x. Want you to compute f prime x, right? So f of x is there, calculate f prime x, and then make sure you verify the necessary condition. Alright, your function needs to change the sign on the interval a to b. At a needs to be negative, then at b it has to be positive, or if at a it's positive, then at b it needs to be negative. Alright, so sign change has to occur. If sign change does not occur, then we don't know if the graph cuts the x-axis. Okay, and then finally choose start the initial point C0, initial 0 C0. As I said, for us the standard choice for C0 would be the left hand point A. Alright, again it's completely up to you what you would like to start this process with. Okay, starting it with C0 will make third or fourth approximation 3 decimal accurate. Alright, and if you want to approximate it even further, then of course you can find 10th approximation, 12th approximation, which is even 8 to 10 digit accurate, decimal accurate. Okay, all right, let's try to see a few examples. So here is the first one: approximate the solution of equation 3x square plus 5x minus 2 equal to 0 on the interval 0 to 1. Instruction says write your final answer to the nearest thousands. Okay, let's try to understand this problem, and I'm going to solve it step by step. Remember, the first step is to make sure that the right side is 0. It is 0 indeed for this equation. All right, so I'm going to skip that first step. I will start with the second step. Label the left side as a function. Okay, so 3x square plus 5x minus 2. Label it as f of x. Step 3, calculate f prime x. I'll be needing that too, right? F prime x is 6x plus 5. Alright, check the necessary condition. Evaluate your function at 0. Looks like if I substitute x equal to 0, I'm gonna get -2, meaning f at 0 is negative. Plug x equal to 1, I get 3 times 1 square plus 5 times 1 minus 2, and this is going to be 8 minus 2, and 8 minus 2, and that is 6, right? So I made that minor error here. It needs to be 8 minus 2, which is 6. Again, point is it's a positive quantity. All right, so function changes the sign, okay, as I move from 0 to 1. Okay, so Newton's formula can be used. I can, write down Cn plus 1, calculate Cn plus 1, nth plus 1th approximation can be calculated using the nth approximated 0. Start with C0. C0, as I said, our standard choice is that left hand point 0. Start with C0 equal to 0. To compute C1, I need two things. Alright, which two things do I need? I need value of my function at 0 and value of its derivative at 0. Okay, let's calculate it. F at 0, that was already calculated earlier, it's -2. F prime at 0, it is going to be 6 times 0 plus 5, and that is going to be 5. Alright, I can now calculate the first approximated 0. C0 minus f of 0 over f prime at 0. Just need to throw the numbers in. C0 was 0 minus I have f at 0 -2 and f prime at 0 is 5. So I get 2 over 5 and 2 over 5 is 0.4. Right? So this is my C1. If I want to calculate C2 using C1, then I need f at C1 and f prime at C1 to be evaluated. Alright, let's do that computation. Look, f at C1, f at 0.4, 3 times 0.4 square plus 5 times 0.4 minus 2. I get 0.48 plus 2 minus 2, that's gonna be 0.48. Okay, f prime at 4 is going to be 6 times 0.4 plus 5. It's 2.4 plus 5, looks like it's 7.5. Alright, ready to calculate C2. C2 is going to be C1 minus f at 0.4 divided by f prime at 0.4. Plug the value of C1 in here, 0.4, and then replace these two things by the corresponding values. I get 0.4 minus 0.48 over 7.5. If you subtract this two entry, you get 0.346. Again, I want my answer 3 decimal accurate, so I'm gonna write down everything in up to 3 decimals. Okay, alright, so C2 is there. In order to calculate C3, I want f at 0.346 and f prime at 0.346. Let's calculate it. So as I said, it's an iterative formula like Euler's method, nothing tricky. Alright, it's all just computation. Okay, let's compute it. F at 0.346, 3 times 0.346 square plus 5 times 0.346 minus 2. Looks like we get 0.359 plus 1.73 minus 2, and the final outcome is 0.089. F prime at 0.346 is going to be 7.076. Plug the values in. C3 is C2 minus f at 0.346 over f prime at 0.346. If you plug the entries in, you are going to get 0.333. Right? So this is, the third approximated solution. All right. You may wonder that where should I stop? All right, I'll tell you just in next 1 minute or so when to stop. Okay, let's compute C4. Well, to compute C4, I'm going to evaluate f at C3, f at 0.333, which is going to give me 0.002. Alright, again I plug x equal to 0.333 into the original function. I need f prime at 0.333 as well. That's gonna be 6.998, and I want you to plug the values in. into the formula, I get 0.333 minus 0.002 over 6.998. Now 0.002 over 6.998, if you use your calculator, you will get this number 0.000285. all right, because we are only considering 3 decimal places, I'm gonna write down only that those 3 decimal places. I realize that I get the same entry back. That means C3 is the one that approximated, that is 3 decimal accurate. Now C4 is 0.333, C5 is gonna be 0.333. Now any approximation that you are gonna do, if you are looking for 3 decimal accurate result, then this is the answer that you are gonna get. All right, meaning that the zero of that polynomial is really 0.333. Now the polynomial that I discussed with you guys, many of you have solved that polynomial in 1325. all right, let's try to see what is the exact solution. All right, it's a quadratic equation. It's a non-monic polynomial, so product of 3 and -2 is -6. I find out the roots of factors of -6 whose sum is 5. Well, 6 and -1, so I'm gonna break that middle term into 2 pieces. Positive 6x minus 1x, they adds up to -5x. Now group the first 2 term, group the last 2 term. Take 3x out from the first 2 term, take -1 out from the last 2 term. Alright, factorize it further, I get 3x plus 3x minus 1 times x plus 2 equal to 0. This means either first factor is 0 or the second factor is 0. I get x equal to 1/3 and x equal to -2. Out of these two zeros, x equal to 1/3 is the 0 between 0 and 1. Alright, what is the value of 1/3? Remember from the last lecture, 1/3 is a fraction and its decimal representation is repeated. All right, 0.333 repeated infinitely many times, or 0.3 bar is the 0 in 01. All right, I want you to compare that with our approximated solution. Very close, right? So that's the beauty of this theorem, right? You don't need to know how to solve the equation analytically. You can still approximate it. All you need to know is find out whether your on what region your function changes the sign from negative to positive or positive to negative. The smaller interval you choose, the better your approximation will be. The faster you will get that approximation. For example, instead of doing 0 to 1, if you would have done like 0.2 to 0.4, then this approximation would have given you 3 decimal accurate answer in 2 steps or so. All right. Anyways, those are just the comments. Don't have to implement it. Let's try one more example. A very interesting one indeed. All right, where function will not be given. Let's say approximate cube root of 3 to the nearest 1000. All right, meaning I need to find out 3 decimal accurate answer. Now, as you know, in the world of calculators and computers, we can easily calculate this number, cube root of 3. All right, but imagine that 200 years back, if somebody would ask you, can you compute cube root of 3, then this would have been a very challenging question. And that is where this Newton's method was arised, right? So this is really a very interesting method that let you approximate various radical powers without using computer or calculators. Anyways, so that is one way to ask that question. Second way is approximate the solution of equation x cube minus 3 on interval 1 to 2. Okay, that second way looks very similar to the first problem, and I'll tell you that how you can obtain that equation from here. Okay, this is something that is very, very important, all right, from the viewpoint of your exam. So be sure you guys know how to approximate radical power of a number. Okay, anyways, let's try to understand that how we are going to solve this this expression. Okay, so I will first start with a very simple observation, that find out two numbers whose cube root is known and they are closest to 3. All right, when I say closest to 3, close from the left side and close from the right side. I know that cube root of 1 is 1, right? And because 3 is bigger than 1, cube root of 3 needs to be more than 1. Another thing that I know is that cube root of 8 is 2. Alright? And 3 is smaller than 8. So cube root of 3 needs to be smaller than cube root of 8. Alright? This is a very obvious and trivial observation. Right? This observation will give me, will show me a path. Let's write down that observation. Notice that cube root of 1 and cube root of 8 are known, and cube root of 3 needs to sit between cube root of 1 and cube root of 2. So whatever my approximation is, it will be between 1 and 2. Okay. Alright, now the question is, how do I come up with the function? Let me show you. Assign a variable for cube root of 3. Okay, so let's say cube root of 3 is x. Suppose x is cube root of 3. Okay, now I wanted to turn this into the equation. In order to turn it into the equation, let's try to get rid of that cube root. Cube root is 1 by 3 power. No, what I want you to do is take the cube on both sides. If you take apply cube on both sides, that cube root and cube will be cancelled from the right hand side. On the left hand side you will get x cube. So you have x cube equal to 3. Alright. Okay. If x cube is equal to 3, then as I said, I am close to my equation. Now apply those steps that I defined earlier. Shift everything to the left side. Make sure that the right side is 0. Alright, so I get x cube minus 3 equal to 0. Now label the left side as a function. You see, that's how I get this equation. Okay, so whatever number you would like to approximate, label it as x. Okay, and then try to get rid of the radical power by applying some integer power on both sides. And once that is done, try to shift everything to the left, make the right side 0, you will get your equation. Now in that equation, I'm gonna label that left side as my function. Okay, I need to calculate f prime x. Let's calculate it. It's 3x squared. Pretty simple, no? I need to check that Newton's method is applicable here. Now region of interest is 1 and 2. We already verified that the approximation, the cube root of 3 is between 1 and 2. So check the sign of your function at 1 and at 2. You will realize that the function will change the sign. Look, f at 1 is 1 cube minus 3, and that is negative 2. It's negative there. F at 2 is going to be 8 minus 3, which is 5, and that is positive. Alright. So we have function that changes a sign from 1 to 2, and function is continuous. So function must cut, x-axis between 1 and 2. If we would like to find out, we would like to approximate where it's going to cut the x-axis. Okay, let's start with C0 equal to that left end point 1. Okay, I need f at 1 and f prime at 1. F at 1 is negative 2, f prime at 1 is 3. I can calculate C1, which is C0 minus f at 1 over f prime at 1. Throw the values in. 1 minus negative 2 over 3. Looks like I get 5 over 3, which is 1.666. Again, I want the approximation 3 decimal accurate, so that's why, I'm only considering 3 digits. Okay, now use the C1 to compute C2. I need f at C1, f prime at C1. So f at 1.666 and f prime at 1.666. Look, f at 1.666, pretty easy to calculate using calculator. Get 1.624. F prime at 666, it's gonna be 8.326. Time to calculate C2. C2 is C1 minus f at 1.666 divided by f prime at 1.666. If you simplify the numbers, you will end up getting 1.471. All right. Using C2, compute C3. To compute C3, I need f at C2, f prime at C2. Here are the values, 0.183 and 6.492. Want you to plug those two values into C3 formula. I get 1.443. What I want you guys to do is verify that the fourth approximation is also 1.443. All right, meaning calculate f at 1.443, f prime at 1.443, and then plug them into the formula and find out, verify that this is also 1.443. Okay, all right. So as I said, examples are simple, and this is really a classical approximation technique to approximate the zero of your function. It's an interesting method indeed. Let's try to wrap up this discussion with one final example, very similar to approximating that cube root. Okay, so let's start with all right, so we can certainly write it as cube root of 3 is nearly equal to 1.443. All right, let's wrap these things up with this final example. Approximate square root 12 to nearest thousandth. Right, want 3 decimal accurate result. First of all, find out between which two perfect number square root of 12 is leaving. All right, so find out the numbers closest to square root 12 whose square root is known to you. All right, not too difficult to classify those two numbers. Square root of 9 is 3, square root of 16 is 4. Because 9 is smaller than 12, square root of 9 will be smaller than square root of 12. And then 16 is bigger than 12, so square root of 16 is really bigger than square root of 12. This tells me that whatever the square root of 12 is, it's gonna be the number between 3 and 4. Okay, so graph of associated function is going to cut the x-axis between 3 and 4. Okay, need to generate the function. You're gonna play the same game. I label that square root of 12 equal to x, and then I will square both sides. Okay, so when you square both sides, you get x square equal to 12. Now shift that 12 over to the left side, you get x square minus 12 equal to 0, and label that left side as a function. Okay, so your f of x is x square minus 12. Find out f prime x, it's just 2x, fairly simple. Now check the necessary condition for Newton's method. I want f at 3 to be negative, f at 4 to be positive, or f at 3 to be positive and f at 4 to be negative. So I want the sign change in my function. Let's check. All right, f at 3 is 3 square minus 12, it's going to be negative 3. F at 4, 4 square minus 12, that's going to be positive 4. So function indeed changes the sign. Let C0 equal to 3. To compute C1, I need f at 3, f prime at 3. Very easy to calculate these entries, right? Calculate the first approximated solution. C1 is C0 minus f at 3 over f prime at 3. Looks like I get 3 minus negative 3 over 6. This is 7 by 2. I get 3.5. Alright, so 3.5 is the first approximated 0. Calculate the second approximated 0 using first one. I need f at 3.5, f prime at 3.5. We have both the values. Now plug them into the formula. 3.5 minus 0.25 over 7, get 3.464. Compute C3, and C3, I realize that f at C3 is pretty small, negative 0.0007, and f prime is very big, right? The ratio is going to be close to 0. All right, I get 3.646 again as I said. So C3 and C2, they are indeed the same number if you consider only 3 decimal places. Okay, so at C2 the process usually terminates. We calculated C3 to confirm that this approximation is 3 decimal accurate indeed, right? We can literally write like square root of 12 equal to nearly equal to 3 point, or approximately 3.464. If you use your calculator to approximate this number, you will realize that the first 3 decimals are going to match perfectly. All right. Okay, so that is the end of the story for today. Again, if there are any questions, any concern, if there is anything that doesn't make sense, then feel free to send me an email. I will be very happy to go over it again. Thank you.